Okay, let's dive into one of the most fascinating and frustrating challenges in all of robotics, the sense of touch. For you and me, it's just second nature, right? But for a robot, it's the final frontier. It's the difference between a clumsy machine and a truly helpful partner. So, what's the secret to getting it right?
Yeah, really, it all boils down to this question. You can effortlessly pick up a raw egg, a slippery glass, or a heavy bottle, adjusting your grip without even a second thought. But for even the most advanced multi-million-dollar robots, this is an incredibly hard problem. So, what's our secret? What do we have that they don't?
At the very heart of this is what we can call the clumsy robot problem. It's this massive gap between our natural biological dexterity and the rigid, pre-programmed world that machines live in. And you can really see that difference laid out here. Our grasp is totally adaptive and intuitive. We feel an object start to slip, and bam, we react instantly without even thinking about it. A traditional robot, on the other hand, is brittle. It's just following a rigid set of rules. So the moment it encounters something new, something it wasn't explicitly programmed for, it usually fails, either by dropping the item or, worse, by applying way too much force and crushing it. And that's the real bottleneck here. This whole grasping problem is the main reason why robots are still pretty much stuck on assembly lines, dealing with the exact same object over and over and over again. It's what's preventing them from being truly useful in our dynamic world, in our homes, in hospitals, basically anywhere that things aren't perfectly predictable.
Okay, so why has this been so incredibly hard to solve? To really understand this new breakthrough, we first have to take a quick look at why all the past attempts have pretty much fallen short. In the early days, they just used grippers with a preset amount of force. That's great for a factory, but totally useless in a kitchen. Then, in the 2010s, we got imitation learning, where a robot tries to perfectly copy a human's actions. But the problem is, it can't generalize. Teach it to pick up one mug, and it has no idea what to do with a slightly different one. Most recently, we've thrown deep learning at it, but that requires just massive amounts of data and often creates what's known as a black box, which, well, that has its own set of problems. A black box AI is basically a system that might give you the right answer, but you have absolutely no idea how it got there. You can't see its reasoning. And when you're talking about a robot that needs to safely handle fragile objects, or maybe even interact with people, that lack of transparency is a major problem. You just can't trust it. And this is where things get really interesting. This brings us to the breakthrough. A team of researchers at Tsinghua University realized the solution wasn't more data or faster computers. It was about looking at the problem completely differently by decoding the secret of our own human touch. And this quote from Professor Rong Zhu just hits the nail on the head. We don't think like computers. We aren't calculating precise force vectors. We think in simple, qualitative states. We just ask, is this secure? Or, uh-oh, is it starting to slip? Our brain takes a whole flood of sensory information and just distills it into a simple, actionable idea.
And here's how our brain does it all in a split second. First, sensation. Your fingertips feel everything. Pressure, little vibrations, sideways forces. Step 2 is abstraction. Your brain filters out all the noise and simplifies the data. That leads to step 3, the interpreted state. Your brain concludes, hey, this object is slipping. And finally, step 4, the reflexive action. Your hand automatically tightens its grip, often before you're even consciously aware it's happening. It's brilliant. So the researchers at Tsinghua decided to teach a robot to do the exact same thing, to abstract all that complex sensory data into simple, intuitive states. And honestly, the way they did it is just fantastic. And check it out, the process beautifully mirrors our own. First, a human wears a high-tech sensor glove, grabbing things and generating all this rich tactile data. Then an AI is trained, not on the raw data, but to classify that data into those simple, grasping states. From there, the robot's own AI can identify a state like highly unstable and use something called fuzzy logic, which is a type of AI that's great at handling imprecision, much like our own intuition, to make a smart, human-like adjustment. And that's it. This is the simple genius of it. These are the only 3 states the robot's AI needs to understand. Is the grasp stable, slightly unstable, or highly unstable? By reducing a potential flood of sensory data down to just these 3 simple concepts, the robot can react quickly and appropriately, just like we do. And the result of this approach is a system that's incredibly efficient. It doesn't need those massive data sets like other AI methods. It can learn from just a single human showing it what to do.
And best of all, the intelligence is transferable. You can train the system with all that human data and then just deploy it directly on a robot. No need to retrain the whole thing from scratch.
So this all sounds great in theory, but how did it actually perform in the real world? Well, the results are genuinely exciting, and they point towards a future where robots can finally, truly leave the factory floor. 95.2%. Just let that sink in for a second. That was its success rate in grasping a whole range of really challenging objects. And we're talking about the exact things that stump other robots: fragile eggs, slippery cups, heavy bottles. It's an absolutely incredible level of performance. And this chart really puts that number in perspective. I mean, look at it. Compared to older methods like imitation learning, which barely gets above 2/3, or even the more modern data-hungry deep learning approaches, this new tactile state method is a massive leap forward in reliability. And to prove its capabilities in a complex, real-world task, the team had the robot make pour-over coffee. Think about that. It had to locate all the tools, scoop the grounds, pour hot water, and stir, all while constantly adapting its grip to different objects. It's a perfect demonstration of real dexterity in a normal, unstructured environment. So, what does all this mean for us? Well, the applications are huge. Think of safer robots that can actually help the elderly at home. Think about healthcare, with delicate handling of medical tools, or even automated kitchens that can prepare food with a human-like touch. This technology could fundamentally change how we collaborate with robots. Look, this is a fundamental shift. By teaching robots to understand the world like a human, instead of just mimicking our actions, we open up a whole new world of possibilities. And that leaves us with a really fascinating question to ponder. If we finally crack the code for intuitive touch, what's the next human sense that robots are going to master?